Hello everyone and good evening. Welcome to AISC's Night School, Bracing Connections and Related Topics, presented by William A. Thornton. Today is October 13th, and this is Session 3, Bracing Connection Details and Prying Action. I want to welcome back our speaker, William A. Thornton, PE and PhD. Dr. Thornton is Corporate Consultant to Surveys Corporation of Roswell, Georgia. He is the winner of the AISC 1995 T.R. Higgins Lectureship Award and the 2003 AISC Lifetime Achievement Award. He has served as an invited lecturer numerous times at AISC and at various state structural engineering associations. He is the author or co-author of many published papers on connection design and other structural areas as well. He served as the chairman for the AISC Committee on Manuals for 20-plus years, and in 2013 he was elected to the National Academy of Engineering. Please welcome back Dr. Bill Thornton. Bill, thanks for being here. I'll hand things over to you.
Okay, thank you, Brent, and good evening or good afternoon, ladies and gentlemen. This is Session 3, Bracing Connection Details and Prying Action. The overall title of this presentation is Bracing Connections and Related Topics, and the special topic tonight is Bracing Connections and Prying Action. You might wonder why that juxtaposition. Well, it should be clear before we're done. This is an outline of what we'll cover tonight, comparison of bracing connection details, and then that will lead into the development of the 14th edition manual prying action method. There are two design algorithms, one's design, one's analysis for prying action, and then we'll go through an example of prying action for a bearing type connection and for a slip critical connection, and then we'll have a summary if time allows. This is a typical bracing connection. We'll look at connection details. We'll look at basically three of them. The first one is with clip angles, as you see here. For this type of connection, you must consider prying action, not just for the clip angles, but also for the column, if we're connecting to a column flange, for example. The clip angles are kind of the first of the three that we'll look at because I would say traditionally they have been around the longest. In fact, clip angles, beam to column connections used to be called the AISC standard connection, standard shear connection. They're not called that anymore. But there's a lot of engineers' drawings and details and notes that still refer to the double clip connection as the standard connection. For this type of connection, prying action needs to be considered. What are the advantages of this type of connection? Well, ease of fabrication. It's commonly used, as I've mentioned, and it easily resists low to moderately high transfer and H sub C forces. Now, the H sub C force is something we talked about either last week or the week before. It's one of the components. It's actually the horizontal component of force between the gusset and the column and between the beam and the column. Ease of fabrication, that is to explain that. I mean, the beam is basically cut short or a little bit shorter than it needs to be. Like there's usually a setback or a proud dimension here of about a half an inch. So if the beam is a little bit long or a little bit short, that could be made up simply by placing the angles on the beam and on the gusset where they need to be, such that the out-to-out dimension of the fabricated piece is correct. What are the disadvantages? Well, if you're connecting to column flanges, then you may need column flanges, which are not, it's not desirable to do. It's expensive to do that. Difficult to use if you have column web stiffeners. For instance, if there are moment connections in the other direction, in the weak axis direction in this picture. There's an upper limit on the available angle thickness unless you fabricate an angle, which can always be done, but available rolled angles are 1.125" maximum thickness. And no matter what thickness you go with the angle, you may run into a problem with the column flange itself. The second type of connection, second detail that's common for bracing connection is the shear plate, or the shear tab. And this particular picture shows a conventional shear tab. Say, by that I mean a single column of bolts between the gusset and the column, and an extended shear tab between the beam and the column. What are the advantages of this type of connection? I'd say the main advantage of this type of connection is ease of erection. There's no prying for the column flange. There's no prying action involved in this particular connection. So we'll look at three details of the three. Two require prying action, and that's why this hour-and-a-half session will cover that mostly. But this one does not. One great thing about it, in addition to the ease of erection, is that it eliminates the need for drilling at thick column flanges. And you saw some slides last week and the week before where this idea was used on a large boiler house job where we avoided drilling, say, 3 and 4 inch flanges by using this type of detail. It's a preferred connection at HSS columns. Facilitates column web connections with stiffeners. For instance, if there's stiffeners because you've got weak axis moment connections, it's somewhat irrelevant for this type of connection. It's on another plane. What are the different disadvantages? Well, it might require multiple lines or columns of bolts. It's not uncommon to see where we've got 2 columns of bolts between the beam and the column here to have 3 or 4. So that plate sticks out there a ways. But that really isn't an issue. It's still fairly inexpensive fabrication, and it's very easy to erect. It may require heavy plate and wells for high forces. The tab well size, 5/8 T, each side of the plate, is not generally required for this type of connection unless you have a specific ductility requirement, as you would have, for example, in one of the 3 ways that you could do special concentrically braced frames. But ordinary non-seismic and ordinary concentrically braced frames, there's no specific explicit requirement for ductility for this type of connection. Slip critical bolts are required if slots are used in the tabs because you're going to have an axial component. The third type of connection is the end plate, and prying action must be considered for this one. End plates have advantages. They can resist really quite high transfer and H sub C forces. You can extend the end plate to engage the flanges. For instance, it could be extended to include the top flange of this 16 by 57 beam. It has few parts. This one shows a single end plate. We could do it with 2 separate plates. Sometimes you need a heavier plate between the beam and column and a lighter plate between the gusset and the column. So you would have 2 separate plates. And that's not a problem either. So it's really quite versatile. What are the disadvantages? Well, it's difficult to fabricate because the beam has to be cut to exactly the right length, or with some tolerance to account for over-rolling and under-rolling. So there's little erection clearance or tolerance. Fillers can be used on one end or the other to account for underrun or overrun considerations. Plates, these plates have a tendency to curl or warp due to the heat of welding, which might compromise your out-to-out dimension on the beam. Prying of the column flange may control the strength. So even if you could go to, say, 1.5 inch end plate here, if the column flange is 3/4 of an inch thick, that could very well be the controlling element, the controlling limit state. So you could see that in the 3 types of details that we've looked at for bracing connections, double clips, shear tabs or shear plates, and shear end plates, 2 of the 3 required prying action. So the rest of the presentation here tonight is essentially to go through what's in the 14th edition manual on prying action. Prying action is mentioned in the 2010 specification. That's the one that's in the 14th edition manual. It was also in the 13th edition manual, and in every specification since the 7th edition manual, about 1970. All it says, though, is the required tensile strength shall include any tension resulting from prying action produced by deformation of the connected parts. If you go all the way back to the 6th edition, which was like 1960 or 61, there was nothing in there at all in the specification on prying action, but the commentary mentioned it. And in the 7th edition, what was in the commentary was put in the specification. And since then, every specification since the 7th has had something in it about prying action, mostly pretty much similar to what you see here. So first, some prying action discussion. If the connected elements are relatively flexible, then prying forces can develop. Part 9 of the 14th edition manual has a detailed discussion of prying action. This kind of shows you the physical situation that we run into when we have, this is say a column flange or a WT. This picture and the subsequent ones are from the bolt guide that's listed down here in the lower right-hand corner. It's the guide for design of bolted and riveted joints. 2nd edition was 1987 by Kulak, Fisher, and Struick. This shows you what's happening. If I have a pretension bolt, say this is a 7/8 diameter bolt, the pretension is 39 kips. Very little additional load is put in the bolt until you reach the point where separation takes place. And at this point, there's essentially the pretension is overtaken by the applied load. So you can see, say, at 60 kips applied load, you'd have about 60 kips bolt force. B sub C being the bolt force here. For a relatively thick flange, this one is 1 11/16, you'll find that there really is no prying. For a thinner flange, though, this one is again from the bolt guide. We have a 3/4 inch flange, and what happens is that as you start loading the bolt up from the pre-tensioned state, you reach a point where an additional force exists in the bolt. So now what's happening is that you might have, say, an applied load here of maybe 30 kips, but when you come up here and look at what you've got, you might have 50 in your bolt. And that the additional force that we're coming up with is called the prying force. B sub C is the total bolt force. It's the applied load or the demand plus the Q, the prying force. It's little q here, but if you go to the bolt guide, 1987, and the first edition was 1974, they used a capital Q instead of a little q, but it means the same thing. Here's the 2 pictures that we just looked at side by side. T sub C is a parameter that will be defined in the course of tonight's presentation. It's the value of the plate thickness for which no prying occurs when the bolt strength, B, is achieved. The available bolt strength, the bolt design strength, is what we're calling capital B in this presentation, and that's what you'll find also in Part 9 of the manual. So we've seen these 2 slides before. You can see the difference. I mean, when you don't have prying, if you got 60 kips applied, you got basically 60 kips of force on the bolt, but when you have prying, it compromises the design because the forces in the bolts are actually bigger than you might think they are by the amount Q. Big Q or little q. Note that these pictures show, I'm coming back to this paragraph here, note that these pictures show connections to assumed rigid surfaces. Generally, T sub C must be evaluated for both sides of the connection. And as I said before, T sub C will be defined in a little while. For instance, if we have a bracing connection with an end plate, like this one, which is similar to the one we just looked at with a shear end plate, you've got prying forces that exist in this connection, as shown on the next slide. The prying force, or the tensile force in the bolts, the tensile demand between the gusset and the beam is 176 kips, and that's also applied then to the flange of the column. And you can see the same 176 kips down here between the beam and the column. It's shown as a compression here because it's a tension up here. But really, if that 840 kips was a compression instead of a tension, then these loads, every one of these loads would reverse, except for the beam shear. The 50 kips will always be in the same direction, assuming that gravity is down. So, what's the probable behavior and simplified model that we use for prying action? It's the Struik-de-Bach model. Struik was one of the three authors of the design guide. It was Kulak, Fisher, and Struik. He's the third author. I think he was a graduate student for a while at Lehigh back in the probably the early 80s or the late 70s. Yeah, the late 70s or the mid 70s, because the book was published in 74. This model, Struik-de-Bach, really was developed in 1969 in the Netherlands at Delft University. The pictures shown here are from the bolt guide. Basically what they found was that the bolt force really doesn't exist at the center of the bolt. It kind of migrates from the center of the bolt to the inside edge of the bolt. And that's picked up in the simplified model that's due to Struik and de Bach by saying that the actual bolt force, the B sub C, which is the bolt force T plus Q, acts at the inner edge of the bolt. You know, D is the bolt diameter, not the hole diameter. I mean, why not the hole diameter? Because the original researchers used the bolt diameter, but it probably doesn't make a lot of difference. Anyway, this is the AISC manual, Part 9. Notation, very similar to what you saw in the previous slides. We have A and B. A, the distance from the toe to the center. B, the distance from the center of the bolt to the face of the web. And A prime and B prime as defined on the previous slide. If we have an angle, the only difference is that B, instead of being measured to the face of the angle, is measured to the center of this leg, the leg that's not subjected specifically to prying, because it could be, you know that there's a setback right here near the heel of the angle, a ½ inch, 3/4 of an inch, more or less. It's possible for the bending actually to take place right here in this leg rather than in the leg where we normally show it. So that was introduced in the 13th edition. This just shows it blown up a little bit. The bolt line, the stem line is the face of the stem, but again, remember, if we were talking about double angles here, it would be going to the center of the leg of the angle, right to here. In notation-wise, we've got double curvature in this area. In the B area here, we've got an M1 moment, say positive at the bolt line, and an M2 moment at the bolt line, positive say, and an M1 moment at the stem line, negative. One is positive, one is negative, so you have an inflection point between the two. Let's derive the equations for prying action. It's really quite simple. This is, again, the Struik-de-Bach model. These pictures that you see here, I believe, were from a paper that I wrote in 1985, but they're very similar to what you'll find in the bolt guide. We've got the three-body diagrams. This is the geometry, the A and the B, sections BB and AA shown here. The little p is the tributary length of fitting, WT in this case, or angles per bolt. And then we have two free-body diagrams that you see over here. Pictures C and D. Delta here is just a parameter that gives us basically the length, the effective length at section BB relative to section AA. So we're taking out 1 minus D prime over P, and D prime is the width of the hole. It's not the width of the hole plus a 16th in the original research, it's the width of the hole. So let's look at equilibrium. If I calculate, if I take this free body diagram C here, this first equation that I have, this one right here with the green arrow is basically moment equilibrium about section BB, right here, this section right here. So if I take counterclockwise positive, I've got M sub C minus T times B plus Q times A equals 0. That's some of the moments for this free body diagram about this section. The second equilibrium equation is some of the vertical forces for diagram C here. So I get T plus Q minus B sub C equals 0. And the third equilibrium equation is moment equilibrium for this little picture that you see here, taking moments about BB again, but now looking at the other part of it. Counterclockwise positive, I get alpha delta M sub C with a minus sign plus Q times A equals 0. This is basically all there is to it. Those are the equilibrium equations. There are no others. We can rearrange the equilibrium equations, the three of them that I had on the previous slide. We go to the Struik-de-Bach model and replace A with A prime, as we saw, B with B prime, and then we just define the ratio rho of B prime to A prime to keep the notation looking neat. And the three equations on the previous slide, these three equations, these equilibrium equations, can be reduced to two. Because you can see that I've got Q, the prying force, big Q here, this is the old notation, occurs in the other two equations. So I will use the third equation here for Q to eliminate its appearance in the first two equations, and this is what you come up with. T times B prime times the quantity 1 over delta alpha equals m sub c, which is the moment at the stem line. And then T times the quantity 1 plus alpha delta over 1 plus alpha delta times rho, this is really kind of the Q term, is equal to B sub c, the total force in the volt. So that's the equilibrium equation. Now what about the limit states? For the flange, m sub c, the moment in the flange, cannot exceed the plastic moment, m sub p. M sub p is 1/4 times f sub y times p, which is the width per bolt times the thickness of the fitting squared, with a resistance factor phi. And for the bolts, this is the spec equation, phi times F sub nt, which is the tensile strength, the nominal tensile strength of the bolt times the area of the bolt. And this box here, which isn't coming up on my computer anyway, it should be an equal sign with an open triangle above it, because this quantity, phi F sub nt times A sub b, is just defined as B. That's what capital B is, the available strength of the bolt, the design strength of the bolt. One change that took place between the 3rd edition, LRFD, and the 9th edition, ASD, when they were combined into the 13th edition, ASD LRFD, was that F sub y in the Prying equations was changed to F sub u. Based on research by Jim Swanson, who was at Georgia Tech at the time, now at the University of Cincinnati, in a paper published in the Engineering Journal in 2002, it was determined that the use of F sub u in place of F sub y gave much better agreement of this theory with physical tests. So starting with the 13th edition manual, F sub y has been replaced by F sub u. The resistance factor phi, however, and the safety factor omega were maintained at 0.9 and 0.75 respectively, because the failure mode in Swanson's test was yield of the T, not the flange. So really what's going on here is some kind of strain hardening so that we get way above just the nominal F sub y up to F sub u. And if you put F sub u in the equations, it turns out absolutely right on the money. And this result actually has been known for a long time, since the early 90s anyway, research that was done at Cornell back in the 60s. If you use that research by Dowdy and McGuire, you would come up to the same conclusion, but it never was accepted by the manual committee because it was using A7 steel, and we didn't really know whether that steel would justify the change from F sub y to F sub u. So it had to wait until we had more recent research. All right, so now introducing, or just repeating the limit states, the F sub y here now is replaced by F sub u. And again, this box here is supposed to be the symbol for defined as. Nothing's changed there. I can now introduce this quantity T sub c, which is defined as you see it here in LRFD terms, 4 times B, the bolt design strength, times B prime, the distance from the edge of the bolt, inside edge of the bolt to the stem line, phi, the resistance factor for the F sub u, and P, the tributary length per bolt. T sub c is the material thickness required to develop the design bolt tensile strength B. And it's either phi times F nt AB or phi F prime nt AB, where the F prime term here is what happens when you've got shear acting on these bolts. And most bracing connections, you will have not just tension on the bolts, but you'll also have shear. Any greater material thickness will not increase the connection capacity. So in a sense, T sub C here is really a property of the system. I've already said this, FNT is the nominal tensile strength of the bolt, and F prime NT is the nominal tensile strength of the bolt modified because of the possibility of shear stress. So if we now take the equations, the equilibrium equations with the limit states, and non-dimensionalize them using the T sub C factor as defined on a previous slide, you come up with these two equations. Inequalities, sorry. T sub E equal to or less than 1 plus delta alpha times the quantity T over T sub C squared. That's for the flange, or the angle, if we were dealing with angles here. And for the bolts, T over B equal to or less than 1 plus delta alpha over the quantity. 1 plus delta alpha times the quantity 1 plus rho. So what the design problem is, or the analysis problem that we have here, is given this information, given the thickness of the flange or the thickness of the angle, given A prime and B prime, which are the parameters that define the geometry of where my bolts are, P, the tributary length per bolt, F sub U, the property of the fitting material, the flange or the angles, and B, the design strength of the bolts. We want to find T and alpha such that we satisfy these two inequalities. T being the demand, the load that we can apply, the required strength, and alpha being the ratio of the moment at the bolt line to that at the stem line. How do we solve this problem? Well, these two inequalities involve equilibrium and the limit states. The solution to this problem is what is called the lower bound solution in the terminology of the lower bound theorem of limit analysis. And now you saw that 3 weeks ago in session 1 where we talked about the lower bound, and I did a three-bar structure and showed you that if you get the true solution that satisfies equilibrium, limit states, and compatibility, you get the peak solution. Well, this is just like that. We're going to satisfy equilibrium, and we're going to satisfy the limit states, but we are not necessarily satisfying compatibility. So we come up with a lower bound solution. So how do we solve? Well, I'm getting ahead of myself here. This is the lower bound theorem. We've already talked about this. Given an admissible internal force field, which is one that's in equilibrium with the applied loads, satisfy the limit states. The two of them here are the bending of the flange and the tensile strength of the bolts. The applied load, whatever we calculate here, capital T, in equilibrium with the internal force field is less than or at most equal to the connection capacity. So here we have, just repeating this slide again, we've got these two inequalities. How do we solve this problem? Well, what we do is we set the two inequalities equal to each other. We make them equalities, and we set them equal to each other. And then we solve what the result is an equation that we can solve for alpha prime, given by the formula here, which is in part 9 of the manual. It's 1 plus delta over 1 plus rho, multiplied by the quantity in the square brackets, T sub C over T minus 1. Notice that all these formulas are in dimensionless form. And this is what you've got. If you now plot T sub B versus alpha, we've got two equations, or inequalities, if you like. I mean, we set T sub B, T over B equal to for the bolts, and T sub B equal to for the flange. You get these two curves. The curve for the bolts is a hyperbola, and the curve for the flange is just a straight line, and they intersect at a point, and that point is alpha prime. And what I've got shown here is what I'm calling the admissible design space. Any point in here is an acceptable design. Anything outside of here is not. The ideal case is what you see here, that where alpha prime is between 0 and 1. But it doesn't always work that way. Sometimes alpha prime comes out to be greater than 1, which means what? That I'm over here now with alpha prime, greater than 1, but I can't really have a physical alpha bigger than 1, so I have to back off from this dotted line to this one to get on the edge of the admissible design space. So now this is my control point, my optimal point, and it's on the flange line. The bolts are up here. They are not fully stressed, but the flange is if I get to this point. So if alpha prime turns out to be bigger than 1, I use alpha prime equal to 1. For this one, if alpha prime is less than 0, and I think there was an error maybe in your handout, and that's shown in red here. I think it says less than 1. It should have been said less than 0, what you see here. Now, here we are at alpha prime. This is where the two curves intersect, and it's at some value that's less than 0. So therefore, I have to move to the right. I have to move from this point to a place where alpha is actually equal to at least 0. So I got to move to the right to this point here. So whenever alpha prime turns out to be some negative number, you use alpha equals 0, and that's basically solving for what's happening at this point right here. And what is alpha prime? There's an alpha in the manual, and there's an alpha prime in the manual. And they're not the same thing exactly. Physically, they're trying to represent the same thing, but alpha prime is the value of alpha, where alpha is the ratio of M1 over M2, M2 over M1 that I pointed out earlier. Alpha prime is the value of alpha for which the design tension per bolt, T available, is a maximum, or the design thickness of the fitting is a minimum. And how do alpha and alpha prime differ? Well, alpha is the actual ratio of the fitting moment at the bolt line, which is M2, to that at the stem line, which is M1, which is shown here in this formula. It can't be used, you can't calculate this number until everything settles down, until you have a design. I mean, if you come up with a number that's 2 or 3 here, it really doesn't mean anything. You have to use the alpha prime to get where we are in design space. This slide just shows you again what alpha is. It's right here. It's the ratio of the moment at the bolt line here to that at the stem line. It's the moment at BB to the moment at AA, and there's a delta involved in that because we have less tributary length actually at BB than we have at AA. This just shows it again, what M2 and M1 is. I keep saying these backwards. M2 is at the stem line, at the bolt line. Did it again, and M1 is at the stem line. Okay, for calculational purposes, you can either calculate M1 and M2 as in a previous slide, or you can substitute the values for those into the formulas and come up with this value for alpha. Alpha is equal to 1 over delta, T over B, times the quantity T sub C over T squared minus 1. Alpha must be between 0 and 1. A value of alpha less than 0 or greater than 1 is physically impossible. You can't use alpha to obtain a design. Once a design is obtained, you can use alpha to calculate the prying force if you want it. By the second formula on this slide, the prying force, little q here, or big Q, the same thing, is B, which is the bolt design strength, available strength multiplied by alpha delta rho times the quantity T over T sub C squared. Again, all of these equations are in dimensionless form. Do we need to calculate the prying force Q? Well, if you go to Appendix 3, paragraph 3.2, calculated stresses shall be based upon elastic analysis. This is in fatigue. For bolts and threaded parts, subject to axial tension, the calculated stresses shall include the effects of prying action, if any. The manual prying action formulation is not elastic. I can't be too emphatic about that. It is clearly not elastic. It's a lower bound solution. It's a limit state solution. If you want to find out if you have to do any fatigue calculations and you need prying action, go to AASHTO, provisions, section 10.32.332. That was an O2. It may have changed. Standard specifications for highway bridges. They give a formula for calculating Q, which is supposedly elastic. I don't know if it is or not, but anyway, it's the one that's being used in the fatigue calculations where prying is an issue. The formulas, I believe, were derived way back at Cornell a long time ago using an elastic analysis. All right, summary of all this stuff on alpha and alpha prime. Unlike alpha, the calculated value of alpha prime does not need to be between 0 and 1. It is a parameter that locates our position in design space. When alpha prime is greater than 1, I mean the physical alpha itself can't exceed 1, so use 1 in the calculations. When alpha prime is less than 0, use 0 in the calculations. When alpha prime is greater than 1, the fitting, the angle, the WT, flange, the column flange, whatever, controls the design. When alpha prime is less than 0, the bolts control the design. When alpha prime is less than 1 and greater than 0, if it's between 1 and 0, both the fitting and the bolts control the design, and this is what I'm calling sort of the optimal solution. For the other two, for alpha prime greater than 1 and alpha prime less than 0, really, one of the two aspects of the connection is not being fully utilized. So in the case of where the fitting controls the design, you could probably use smaller bolts. In the case where the bolts control the design, maybe you could use a thinner fitting. But generally, we don't do that. We just find out where we are and we move on. So let's look at the design algorithms. There are two of them. There are two design algorithms in the manual Part 9, and I don't think these are really clearly delineated in Part 9, but this is what we were trying to do when we wrote that. There's two procedures: analysis, this is what I just did, and design, which is developed in a manner similar to the analysis procedure, but I'm not going to go through it here in detail. You can see my 1985 AISC Engineering Journal paper for more information on that. We're just going to use it here. So the analysis procedure. This is given a thickness, given a fitting thickness, and the dimensions, A and B, and A prime and B prime, and the tributary length per bolt, and the strength of the fitting material, and the strength of the bolt. What we're looking for is, what's it good for? What's the design strength? What is the maximum possible value of the applied tension per bolt? And how do you do that? You calculate this alpha prime that we've been over. You see exactly where that comes from now. If alpha prime is less than 0, you set it equal to 0, and the T available is B. All these parameters here, T, etc., and B, these are per bolt. So this is the strength, the available strength is the strength of a bolt times the number of bolts. If alpha is bigger than 0 and less than 1, this is the formula. And now in this case, both the angle or the WT or the flange or whatever, and the bolts, they both control. So this is sort of, you're using material to its optimal, in its optimal configuration. And if alpha prime is greater than 1, then the fitting controls the bolts. The bolts are too strong. This is the formula T available, the available tensile strength, the supply is the bolt design strength times T over T sub C squared times 1 plus delta. There's an alpha prime in here, which you don't see because it's equal to 1. But then for the design procedure, this is sort of the reciprocal. In this case, we're given a load. We're given a required strength, an applied tension per bolt. We're given the A and the B, A and B prime again, P, tributary length per bolt, the strength of the fitting, the strength of the bolts. What we're looking for now is what's the smallest value of T that will work, that will carry this required load, this required strength, such that equilibrium and the limit states are satisfied. We have equilibrium and the limit states, lower bound solution. What's the solution? Check that the demand, the required strength, is less than the design strength. If so, proceed. If not, you can't go on. If this is not the case, then the applied load, the required strength exceeds the available strength, and you got to use either more or bigger bolts. You can't proceed. Once you have that satisfied, then you can calculate this beta quantity here, which is B over T minus 1 times the quantity 1 over rho, and if the beta is equal to or greater than 1, set alpha prime equal to 1. And if beta is between 0 and 1, and beta can't be less than 0 in this case, the way we defined it, B's got to be greater than T, then alpha prime is equal to the lesser of 1 over delta beta over the quantity 1 minus beta and 1. If you want to see where these come from, go to the paper. I mean, it's basically derived in a similar way to the way I did the analysis procedure. Once you get the value of alpha prime, from which we just did, then you can calculate the required thickness, T, given T sub C, which is a parameter of the system, the load per bolt, the required strength over the design strength over the quantity 1 plus delta alpha prime. Both algorithms will provide the same required connection. You can't do it one way and get one answer and do it another way and get another answer. The analysis algorithm is transparent as to the meaning of the various values of alpha prime. In the design algorithm, alpha prime is equal to alpha if T min happens to be the actual thickness used, otherwise alpha prime is bigger than alpha. Anyway, let's do an example now of this. We'll do 2 examples. And in subsequent sessions of this night school, we will go through a number of examples using what we just presented here. Most of these examples will have some prying action. Next week, we'll have a connection that has double clips, one of the 3 options that we had, and we'll be going through all of the aspects of the design of that connection. Tonight, I'm interested mostly in just demonstrating prying action. So this example and the following one, there's 2 of them here. One's bearing, the other slip critical. We'll present only the limit states associated with prying action. So don't get misled by this. We're not doing everything. We're not doing block shear. We're not doing tear out. We're not doing bearing. We're not doing any of that stuff. All we're doing is the limit state of prying action. And we'll do it for a simple shear connection, and we'll do it for a bearing type and a slip critical connection. Here's the example. This is a beam, an 18 by 50. It's got a double clip on it. The clips are 2 angles, 5 by 3.5 by 5/8. It's 8.5 inches long. The gauge or the cross centers, 6.5 inches, are pretty much a standard gauge. It happens to be cope, so this is a connection to a carrying beam. There's another beam in here between this, and there's another beam on the other side of the web where the green arrow is. Perhaps it's a W12 on the other side, so I have a 3-row connection with the 39 kips in it. So I'm matching this 3 rows here to what's happening on the other side. So let's continue. This connection is subjected to 33 kips shear and 39 kips axial load or normal load. The bolt shear, V, that's the shear per bolt. I work all these problems in per bolt, and then if I have 3 bolts or 4 bolts or whatever, I just multiply by the number of bolts. But capital V here is the shear per bolt. So I got 33 kips divided by 6 bolts, 3 on each side, 5.5 kips. The bolt shear design strength is from the specification table J3.2, or more simply table 7-1 is 17.9. This notation here, the little r sub v, is the shear design strength per bolt. So 17.9 kips greater than 5.5. Okay, so we're good to go so far. For the tension, capital T is 39 total divided by 6. So I've got 6.5 kips per bolt. The bolt design tension strength is 29.8 kips per bolt per manual table 7.2, or again, you can go to specification table J3.2. So the bolt tensile strength, 29.8 greater than 6.5. We're good to go. You might say, well, man, we're alpha good here, right? We got 29.8, we only got 6.5, so maybe we got like 4 or 5 times what we need, but just wait, let's see what happens. The previous 2 slides are preliminary to the prying action checks. If the shear per bolt, if the required shear per bolt were greater than the design shear per bolt, or the required tension per bolt were greater than the design tension per bolt, the connection fails. We can't go on. We cannot go any further than this. We need to either use bigger bolts or more bolts, but we cannot proceed. But in this particular case, we satisfied those 2 requirements, so we're good to go. For bearing bolts, the interaction equation is given in specification section J 3.7 by the formula that you see here. F sub nt prime, or F prime sub nt, equals 1.3 fnt minus fnt divided by phi over fnv times little f times rv sub rv equal to or less than f sub nv. That last part here, this is simply saying that no matter what you calculate here, it can't be bigger than that. F sub nt is reduced to F prime sub nt by the bolt shear stress. And the most interesting prying action problems, and almost every one of them that you're going to deal with in a bracing connection, is going to be a situation where you're dealing with shear, tension, interaction, as you see in this simple shear connection. This is a diagram that shows the previous slide. This particular equation right here is the middle of this. The equation of that line, where I've got the green arrow, is given by this. It's sort of the heart of this. This line is the maximum tension that I can have, the tension capacity, the tension design strength, and this vertical line over here is the shear design strength. So there's really three straight lines that make up the combined shear and tension interaction equation for bearing. This is the one given in the manual, but this one right here is that one up there, and you really can't exceed the shear capacity, which is built into this little f sub rv. I mean, if little f sub rv were bigger than this number, we'd be out here someplace. We're dead in the water. We can't go on. So let's continue. We got 3/4 inch A325N bolts. This interaction equation that we have here is exactly the form needed for the prying calculations, because we need to know B, the bolt design strength, as a function of the bolt area and as a function of whatever the shear is that's applied to it. In this particular case, we have A325 N-type bolts. The F sub N T is 90. The F sub NV is 54. We had 33 kips total shear divided by 6, which gave me 5.5 kips per bolt. And this quantity in here is the area of the bolt. It's 0.442. Doing that calculation and multiplying it by the resistance factor of 0.75 gives me 67 KSI. Note that this 0.75 times 90 is 67.5. That's bigger than 67.0, so I'm okay. If this number here came out to be 69, I couldn't use more than 67.5. So what's the tension capacity, or the design strength per bolt? It's phi F prime sub NT times A sub B, 67 KSI, which is F sub NT prime times phi times the area of the bolt, gives me 29.6. Therefore, 29.6 greater than 6.5, we're still well in. How about now prying action? The geometry. A is the distance from the toe of the angle to the center of the bolt. So it's just using the calculations that you see here. The angle leg is 5, so it's 5 plus the thickness of the web, which is 0.355, minus the cross centers, and divide that by 2 gives me 1.93 inches. And B is the distance between the center of the hole and the center of the other leg, as you can see right here, where the green arrow is. So B is equal to the gauge, 6.5 minus the web thickness, minus the angle thickness. There's two of them. There's one top, one bottom. And then take half of that to get the distance between the center of this leg and the center of the hole, 2.67. P, the tributary length for bolt. The angles I told you were 8.5 inches long, and there's 3 bolts. So the average tributary length per bolt is 2.87 inches per bolt. Therefore, delta is 1 minus the hole diameter, which is 13/16, over P, the tributary length for bolt, gives me 0.713. There's a check that Fisher, Struick, the book, and the original research done at Delft they found that if A was really too big, I mean, if I had something sticking way out here, it really wasn't very effective, that the maximum effect of A is 1¼ times B. So we have A equals 1.93, and 1¼ B is 1.25 times 2.76 gives me 3.45, which is greater than 1.93. Use A equals 1.93. So B prime is B minus half a bolt diameter. A prime is A plus half a bolt diameter. Rho is the ratio of B prime over A prime. 1.03. The parameter, T sub C, is 4 times B, the bolt strength, the bolt design strength, multiplied by B prime, divided by the resistance factor, 0.9 for F sub U, times P, which is 2.83 times 58, square root of that is 1.38. So, T sub C, again, I'm repeating this, is the material thickness required to develop this much strength in the bolt, 29.6 kips. We've got a lot less than that, so we really don't have to go this far, and we don't. You know, we have 5/8 clip angles. We don't have 1 3/8. Any greater material thickness will not increase the connection capacity. It just wastes material. So, calculating alpha prime in the way that we presented here, the intersection of the two curves. Alpha prime is T sub C over T squared minus 1, and out in front we got 1 over delta, 1 plus rho, gives me 2.68. That's greater than 1, so we're going to use alpha prime equals 1. So here we are in design space. The intersection of the two curves occurs out here at 2.68. That's bigger than 1, so I have to back off to the left to get down to 1. So this is my control point. This is my design point. I use alpha prime equals 1. Substituting into the formulas in that case, there's an alpha prime in here that you don't see. It's equal to 1. This is the formula for the T available, what the design strength. T, the thickness of the angle, 5/8, 0.625, divided by T sub C, quantity squared, times B, 29.6, multiplied by 1 plus delta, alpha prime equals 1, gives me 10.4 kips per volt. So the available design strength, 10.4, greater than 6.5, we're okay. So you can see we started out here really with 29.6, and I said earlier, well, that's hell for good compared to what we need, 6.5, but now we're getting a lot closer, aren't we? If you try this, why don't you work this example as a homework problem? Try half-inch angles. Instead of 5/8, try half-inch angles and see whether or not this is bigger than that. I don't think it is. I think 5/8 is the smallest angle that you can use here. It would be nice if we could fabricate our own angle. We could come up with the thickness that we need. But 5/8 is what we're stuck with. Well, maybe there are angles to the nearest 16th. I don't know. We never use them. We use quarter. We use sometimes 5/16. We use 3/8. We use half, and we use 5/8, 3/4, 7/8. 1. There's other angles, but those are the ones that most fabricators stock. So, the prying action calculations for this example are now complete. For information, if you really want to find the value of Q, you can calculate alpha by the formula that I gave you early. It's T over B times T sub C over T quantity squared minus 1 multiplied by 1 over delta gives me 0.99. If I substitute that into the formula for Q, the prying formula, this is B out in front. This is delta, alpha, rho, T over T sub C squared gives me 0.441 kips for the actual prying force. So, is T plus Q less than B, which it has to be? Is 6.5 plus 0.441, which equals 6.94, less than 29.6? Well, obviously, yes. And it always will be. The prying force Q is implicitly included in the prying calculations in the equilibrium equation. The value of Q is never explicitly required for the AISC manual calculations. The Part 9 says this. A lot of people like to calculate it anyway. They just want to know what it is. Except for fatigue. And really, you can't use this theory for fatigue anyway. So, the solution to the analysis problem resulted in an available tensile strength, T available, of 10.4 kips per volt. Now, suppose that we were given that as a required strength rather than a design strength. That's now the load. Suppose we want to determine what thickness of angle is required to carry this tension, this required strength, this load of 10.4 kips per volt. So, with capital T equal 10.4, what little t is required? What thickness of angle is required? Using the design algorithm, we calculate the quantity beta. Beta is equal to 1 over rho times b over t minus 1 gives me 1.79. Since beta is bigger than 1, we set alpha prime equal to 1, and we calculate t. This is the least thickness that'll do the job. If the required strength is 10.4 and the bolt strength is 29.6, it's the square root of that, multiplied by the square root of the quantity 1 over 1 plus delta. There's an alpha prime in here, but it's 1. Square root of that, multiply those together, multiply them by t sub c, 1.38 gives you 0.625. So, note that the angles are, in fact, 5/8 and 6. So if we start with 10.4, we end with, and we started in the analysis with that thickness, 5/8. So we got this as the strength. If we start with that as the required strength, we come back to 5/8 being the required thickness. So you can see that the analysis and design algorithms are, in fact, reciprocals of each other. They give the same result. There's no way that you can use one procedure or the other procedure to get a different answer. And remember that you really can't use alpha. You need to use the alpha prime equations to do this. All right, that's one of the two examples that I want to do tonight. The second one is shear and axial for a slip critical connection. And the following is abstracted from a paper by myself and Larry Muir that was published just 2 years ago in the AISC Engineering Journal. The interaction equation for slip critical connections is given in the AISC specification sections J3.8 and J3.9. This term here is from J3.8. That is the slip critical shear strength of the bolt, the design shear strength of the bolt. This quantity in the brackets here is from 3.9. In the specification, it's called K sub SC. In the bolt guide itself, and the bolt specification itself, RCSC, it's really written pretty much the way I've got it here. This extra term I'm going to talk about in a minute. Let's define all the terms that we're talking about here. Phi R prime V is the strength per bolt, the shear strength per bolt that's reduced because there's an applied tension now per bolt, T, or a required tension per bolt. T sub E is the expected mean bolt pretension. It's D sub U, which is 1.13 most of the time, although it could be bigger than that depending on your installation method, times T sub B, which is the pretension of the bolt, given in table J3.1. T is the applied tension for bolt or the required tension for bolt. And phi R sub V is the bolt shear strength, manual table table 7.3, 7-3. That's the nominal shear, slip critical shear strength, including hole factors and slip factors and all of the quantities that go into the specification J3.8. And this phi R sub T is the bolt tension design strength, which you can get from manual table 7-2. Or you can go to the specification for it too. Now this term here at the back is not part of the specification, but it's necessary because for A325 bolts, the bolt tensile strength is based upon 120 KSI, whereas T sub E is based on an ASTM tensile strength of 105 KSI for bolts of diameter greater than 1 inch. Therefore, If I have a 1 1/8 inch A325 bolt, the design tensile strength is 67.1 kips per bolt. And T sub E, the effective pretension, is 1.13 times 56, which gives me 63.3 kips. Now, suppose that the required strength per bolt were greater than that number, were greater than 63.3. If that's the case, then this quantity here, 1 minus T over T sub E, is negative. If T is bigger than 63.3, and it could be, because all it needs to be is less than 67.1. So if I'm 65 in here, I'd have 65 over 63.3. I'd have that subtracted from 1. It's going to give me a negative number, which is impossible. So you need to include this. This is in the process of being fixed, or at least I think it is. In the ASTM specifications, I don't know exactly why this happens, but the ASTM drops the strength down to 105 for 1 1/8 and bigger, but AISC uses 120 all the way up to 1.5 inch bolts. So there's a disparity here. Okay, this interaction equation gives a reduced bolt shear strength caused by the bolt applied tension load, or the bolt required tension strength, T. For bearing connections, the interaction equation gives a reduced bolt tension strength caused by the required bolt shear. And there's a reason for the two different forms of interaction equations. Here we have reduced shear because of a tension. For the bearing type connection, we had a reduced tension because of a shear. Okay, the next slide is a little busy, but it explains why there's a difference between the two interaction equations. For slip critical connections, all of the shear, until slip occurs, is carried by friction on the faying surfaces. Therefore, applied shear has absolutely no effect on the bolt tension strength, the bolt design tension strength, until slip occurs. On the other hand, any applied tension to this type of joint has an immediate effect on the connection shear strength, because the faying surface compression is reduced with an accompanying reduction in the joint shear strength. The bolts have yet to see any shear load. It is all carried on the faying surface. This is why the slip critical interaction equation is written as the effect on shear strength that is caused by tension, rather than the effect on tension strength that is caused by shear, as in a bearing joint. So there's a big difference between these joints. So what's the design procedure for slip critical bolts? Step 1, calculate the slip critical shear strength as reduced by the applied tension, by the formula that you see right here. Given an applied tension, that's a required tension. This is the expected pretension, 1.1 times T sub B from the table in the manual. Subtract that from 1, multiply it by the shear strength of a slip critical connection that's got without tension. That's the one that involves the mu factor, like 0.5 for surface class B and 0.3 for surface class A, and includes a whole bunch of other stuff like hole factor and that sort of thing. It's all in specification section J3.8, which I am not getting into. And here you have what we just talked about, that T can't exceed the smaller of these two numbers. This is only true, really, for A325 bolts. For A490 bolts, this is not an issue, because ASTM and AISC have the same F sub U values for all sizes of A490s. Step 2, if the reduced shear strength is less than the required shear strength, where V is the shear load per bolt, or the required strength per bolt, the slip critical strength is insufficient, and the connection fails. You need to use more or stronger bolts. You're dead in the water right at this point. If the design shear strength is greater than the required shear strength, the connection is in the pre-slip state. The connection is checked for prying as a bearing connection. This completes the design calculations. Let's look at an example. Shear and axial example, slip critical connection. Now we've got bolts that are A325 SCAN. And when you give a slip critical connection, you need to provide this because it's ultimately going to be checked as a bearing type connection. And I need to know, or the designer needs to know, are the threads included or excluded? So you need to have an N. Slip critical, class A, you need to know what the surface prep is, and you need to know the position of the threads, even in a slip critical connection. So all of the data is given here. But the bolts in the previous example, B, what I just said, slip critical AN, 3/4 diameter, standard holes. We can look up the shear strength of the bolt in table 7.3. It's 9.49 kips per bolt. The required strength per bolt is 5.5. The required tensile demand or strength per bolt is 6.5. T sub E is 1.13 times 28. That's from table J, I think 3.1. It's the pretension of the bolt, 31.6. Step 1, calculate F of phi sub R prime V. So, phi R sub V, R sub T is 28.9, manual table 7.2. T is 6.5 kips per bolt. That's got to be less than the minimum of these two. And the minimum is 29.8, so we're okay on that. Then we have to calculate T over T sub E, 6.5 over 31.6, subtract that from 1, multiply it by 9.49, which is the shear strength per bolt without considering any tension. Gives me 7.54 kips per bolt. That is greater than the applied or the required shear per bolt, which is 5.5. Since 7.54 is greater than 5.5, the connection is satisfactory for slip. It now needs to be checked for bearing. Step 3, the connection is in the pre-slip state. It now needs to be checked as a bearing connection. And the calculations that we do from this point on are exactly the same as we've already done for this connection. It's in the pre-slip state. We now check it for bearing. And this completes this design example. And so, summary. Clips, shear plates, and end plates are commonly used at bracing connections. Clips at bracing connections facilitate the ease of fabrication. We talked about all these things. Typically, you need to consider prying at clip connections to column flanges. Shear plates at bracing connections facilitate ease of erection, particularly that. Shear plates eliminate the need to drill through thick column flanges. End plates, shear end plates at bracing connections minimize the pieces. They have less erection tolerance, though, at end plate connections. We went through 2 algorithms for prying. One for analysis, that is, given a fitting thickness, what's it good for? What's its design strength? And the second one is given a required strength, what thickness do you need? What hardware do you need to make it work? And these were shown to be reciprocals of each other. I mean, if you start with one, you get a design strength. If you take that as a required strength and work backwards, you'll get exactly the thickness, the required thickness of fitting that you started with. The difference between alpha and alpha prime was explained, and I don't know how many times this has come up in questions to the Solution Center and to me personally. I think that if you understand what I've said here about the two of them, you should be absolutely clear on the difference. Interaction of shear and tension in bearing and slip critical connections was explained. I've worked 2 examples. Examples have been worked for the shear tension interaction case, one for bearing and one for slip critical, since this must be considered when designing bracing connections to column flanges. Every bracing connection you look at is going to have a shear and an axial on the connection between the beam in the column and the gusset in the column. And so that brings us to the end of this presentation. And I guess I thank you for your attention, and if there are any questions, I'll try to answer those. Brent, are you there now?
Yes, I am, Bill.
Hey, Brent.
All right. Let's address some questions for this evening. First question. What would happen if there are column stiffeners? Does this help against prying action?
If there are column stiffeners, you would need to have a stiffener. If you could probably eliminate prying action, but in order to do that, you would have to have a stiffener, I think, between every pair of bolts. Maybe between every other pair. I've not really looked into that, but you can't just have a stiffener, let's say, at the top of the connection, at the bottom of the connection, because you got all those bolts in the middle. So, I mean, this might happen, for example, where you've got a moment connection that frames to the column web that's exactly opposite the beam to column connection that frames to the flange. So you might have a stiffener right there at the top, and a stiffener right there, maybe near the bottom, if the beams on the weak and the strong axes are about the same depth. I don't know. I don't think there's any good way to treat that. I don't really feel comfortable with it. I think that I would design the thing as though the stiffeners were not there, just to be on the safe side, or I'd have to have a whole series of stiffeners so that every bolt in the beam to column connection has got a stiffener between each pair of bolts. So I don't think that's going to be a big help. Okay, next.
Okay, I'm going to go back to slide 37. This question references slide 37 and 39. How does the P term, which I actually don't see here, one second. Oh, here it is. How does the term P differ from the yield line theory?
How does the term P differ from the yield line theory? Well, if you like, there's a yield line theory associated with this. The yield line is basically the length of the connection. Let's say we're talking about the angles in the one that I worked. The yield line would be 8.5 inches long, and you would have a yield line at the bolts, and you'd have a yield line at the toe of the angle, or a yield line at the you'd have a yield line at the bolts, and you'd have a yield line at the junction between the two legs of the angle, more or less. So I mean, it really is yield line theory here, but we're not really talking about it that way because it's a very simple yield line. If you had a continuous column, maybe that's the question. If you had a continuous column, I mean, the clips themselves are discontinuous, 8.5 inches long. But if the example that I did here was, say, to a column of 14 by 90 that was continuous above and below the beam, then you could use some additional part of the column to actually increase P here to a P effective. And that will be discussed next week in the example that we're working. Maybe that's what the question is looking for here. The P here is for the angles. On the other side of the connection, if we were connecting to a column flange, we might be able to get by with more than just, 2.83 inches per bolt, because you'd have the column, you'd have a yield line situation where you've actually got something above and below. Okay, maybe that answers the question. If not, maybe give me another shot at it. But what's the next question, Brent?
I've got confirmation. That's what the questioner was asking for. So thank you.
Okay.
I'm going to slide back to the beginning. This would be the connection with the end plate. A couple questions here. Is there a minimum gap between the plates or members in order to not need to use fillers or shim plates?
I don't think that there's anything specified in that regard. I think various fabricators have their own techniques. I mean, columns generally are perhaps a bit overrolled. Maybe they're underrolled, but not by that much. But then you got tilting of flanges and all of that sort of thing to deal with. Then when you weld this thing, the plates themselves are going to curl up a little bit, maybe get maybe compromise the distance between the column flanges from one side to the other. Well, the short answer to the question is not to my knowledge. There's nothing published that I know of on how you should exactly detail this. We've had jobs where we didn't do anything, and we ended up with buildings that were wider at the top floor than they were at the bottom floor. And that's really, you don't want that to happen. I mean, if it's an inch or so, yeah, maybe nobody really notices it. But I think that it was Paxton and Veerling, or maybe I shouldn't mention any names, but some of the fabricators out there have got kind of proprietary ways to handle this kind of thing so that the building goes up square. But there's nothing published that I know of.
Okay. And then, in addition, here's another question about the end plate connection. Is it fair to say another disadvantage is having to drill through the column flange?
Absolutely. That was one of the things I think I said for the end plate. I mean, it double clips end plates. You've got to drill column flanges. There's no question about it. And if you're talking about a heavy job with 14 by 500 odd columns, you're talking about 3 or 4 inch thick flanges. That's a lot of drilling. Okay. You can really avoid a lot of fabrication time by using shear plates in those cases, as you saw in the series of slides 2 weeks ago, and to some extent in the very first session, where I said one of the jobs that we did where we had a couple of power plants and we convinced the engineer to use shear plates instead of double clips, and the uniform force method, and what has been dubbed special case 4 in this presentation, and we saved, according to the engineer, not according to anything that I've said or my employer has said, but rather the customer said that the job came in $2 million less than what they estimated it to be, and he attributed to the things I mentioned 2 weeks ago and 3 weeks ago. No double clips, no end plates, no drilling of heavy columns. I mean, maybe we had to here and there, but we tried to avoid that, and we used shear plates almost everywhere.
Okay, so along those lines then, the question is, of these 3 details, which is most economical? Your answer would be what?
The shear tab, I think, is the most economic. I think it's the easiest to fabricate because you don't have to drill columns. You can avoid all this discussion of prying action. And it's easy to erect. It's very, very simple to erect a bracing connection with shear plates, with the shear, not the shear end plates, but the shear tab kind of plate, because the connection, the beam with the gussets and everything attached can be brought in laterally. There's no issue of sliding it down the column if it's going to a column web. There's no issue of cramming it between the column flanges. If it's going to column flanges, you can just kind of slip it in sideways and get a drift pin on each end, and then maybe a bolt in each hole, or a couple of bolts at each end. Then the erection crew moves on, and the bolt-up crew comes by and puts all the rest of the bolts in. Really works slick. I mean, it works just the same way for beam to column without the bracing connections. We've had erectors tell us that we could save, they would give us a deduct of $50 a beam if we could convert a job from double clips to shear plates, to shear tabs. Generally the conventional shear tab. It's just a lot simpler to erect.
Okay. Next question. If you had more than one, if you had multiple columns of bolts on an end plate connection, for example, how would this affect the behavior of the connection? How would the outer column of bolts affect the prying action analysis?
Oh, we're talking about, let us say, shear end plates?
Yes.
With, let us say, four columns of bolts, two columns that are close to the web of the beam and to the gusset plate, and another two columns of bolts which are outboard of those two, because we've got a column flange that's wide enough that we can get four bolts across.
Yes,
the question
correct.
is how are the outer bolts affected by prying?
Correct.
I would say that in our procedure for that, in my way of looking at this, only the inside two columns take the axial force. All four columns of bolts will share the shear, but only the two columns of bolts that are closest to the beam web and the gusset take any of the axial force. The other two take nothing. There's no way that you can argue that the axial force can get to those two outer columns of bolts unless you use stiffeners. And certainly we do not want to do that because it's very expensive.
Okay. All right, here's another question regarding bracing connections coming into the column web. When dealing with braces connecting to the column web, is the yield line theory appropriate?
Well, for bracing coming into a column web, there wouldn't be any prying action for that unless you have a transfer force, in which case there would be prying action on the clip angles or the shear end plate, if that's what we're using. And then you would have to do some sort of a yield line analysis on the column web. Yes, you would have a yield line analysis on that column web. There's been some papers published on that sort of thing, but you would definitely have a yield line analysis if you got a transfer force. If you're connecting to a column web with a traditional column web connection where E sub C is 0, then there isn't any normal force on the web. And even if you have a special case 4, there's still no normal forces on the web, because by the time you get there, they dissipate. You have normal forces out where the bolt lines are, but by the time you get to the face of the column web, there are no axial forces, unless there's a transfer force. There's some kind of a force that's coming from the other side of the column. Then you would have to consider some sort of a yield line, and there's so many variations on that that I think you need to look at each case on its own merits.
Okay. Next question. How can prying action be addressed with double angles welded to the column?
How can prying action be addressed with double angles welded to the column? Like, say, welded to a column flange, maybe? I don't think that you should. I don't think that you should use that type of connection, because you've got wells way out at the toes of the angle. Say we're talking about double angles. You're going to have wells out at the toes of the angles. A very ineffective way to carry any kind of an axial force, an H sub C force or a transfer force. There wouldn't be any prying action per se, but there would be a normal force on the weld, and because of the bending of the angle, there'd be a couple on that weld too. And there's nothing published on how to handle that. I would not use that type of connection.
Okay. A couple of questions regarding column to base plate connections. Can this methodology be used to evaluate prying action for a column base plate with anchor bolts?
Well, if we're talking about a gusset to a column flange at a base plate, there's a way to handle that with an axial force, with a horizontal force like an H sub C force, as we've defined earlier on the uniform force method, but it's really not quite the uniform force method. But yeah, I would I would treat prying action in that case. And in this forthcoming design guide by Larry Muir and myself, there's an example that does exactly that. If it's to a column flange, if you're talking to out to a column web, then there wouldn't be any normal force to the web. So you wouldn't have any prying at all in that case. We really have not discussed that in this session so far. I'm thinking that probably session 8, which is going to be kind of a pickup session, where I want to talk about a number of things. I don't think we've really quite specified exactly what they'll be, but development of fills is one of them. And the other one that we talked about, or might have mentioned, maybe you mentioned it, Brent, will be gusset plates to column base plates to either column flanges or column webs. But we're not talking about seismic. We're not talking about design of the anchor rods and all that. Just the connection between the gusset and the column and the gusset to the base plate. If you want to know how to design one of these things as a moment connection, as a moment base, I'd say that is really up in the air right now. I don't think anybody really has published anything that is definitive on how to do it, but there are people working on it on the East Coast and on the West Coast. Okay?
Okay. All right, I'm going to move to slide 53. Your discussion of Q, and the question is, which values will give you a higher prying force Q, the elastic method or inelastic or plastic method?
Well, the method that's given here in the manual is inelastic or plastic. You know, I don't know the answer to that. I'd have to go back and look at what this AASHTO provision gives. It's been so long that since I've looked at it that I don't remember exactly what it says or how to do it. But that's something that I'll take a look at, Brent, maybe for next week if I can remember it, and if we run out of other questions to answer, maybe I can take a shot at that. But right now I don't know the answer to the question.
Okay. All right. Well, I think that about does it for questions. We're out of time. We do have a couple more questions that we've not gotten to. So we'll follow up with those individuals with those questions we didn't get to as we finish up here tonight for this evening's session. So I want to thank you again, Bill, for a great presentation. Thank you all for joining us tonight. A lot of good